Now we'll talk about modern theory. So, the atomic theory is this idea that all matter is composed of atoms. And the theory came out of several laws and lots of observations. The law of conservation of mass, we've talked about that one, and also the law of definite proportions and the law of multiple proportions. So the law of conservation of mass says in a chemical reaction, matter is neither created nor destroyed, and this was formulated in 1789 by Lavoisier. So when a chemical reaction occurs, the total mass of stuff involved in the reaction doesn't change. If you take all the reactants and measure their mass, you let the reaction go, and then you measure all the products, including any leftover reactants, the mass is going to be the same. This is, the conclusion he came to after burning things in closed containers. And this is consistent with atomic theory because atomic theory says that in a chemical reaction, what you're doing is you're taking those little atoms, the building blocks, and you're just rearranging them. It's like you're taking a Lego house and you're taking it apart and making two trees out of it. But you still have all the same bricks, right? All the atoms are still there, they've just been rearranged. Any questions? It's a real important idea. So a couple of examples here. So this is sodium metal. It's soft enough that you can cut it with a table knife, but this person's wearing gloves because it's also extremely reactive. So here's solid sodium, it's just sodium atoms, and this yellowish gas here is chlorine, the element chlorine, which is a gas at room temperature. And so that's what the chlorine looks like. When you put these two together, they have a chemical reaction and they form sodium chloride. So sodium chloride is alternating sodium and chloride ions. If you take the mass of sodium and the mass of chlorine that reacted and add that together, in this example, 19.6 grams, and if you measure the amount of sodium chloride produced, also 19.6 grams. Mass doesn't change in a chemical reaction. We say mass is conserved. There we go. Okay, so let's think about this. When a log completely burns in a campfire, the mass of the ash is much less than the mass of the log. What happens to the matter that composed the log? We've got three choices. Anytime you're doing multiple choice, you should read all the choices before you pick one, even if the first one seems right. So A, the matter that composed the log reacts to form gases that are released into the air. B, the matter that composed the log is converted into energy. Or C, the matter that composed the log is still present in the ashes but has a much lower mass. So what do you think? I think I heard someone say A. A is the correct answer. So the ash left in the fire pit weighs a lot less than the log. So it's tempting to think that, well, it just decreased in mass, or maybe that mass was converted into energy. But what you can't observe with your senses is that a lot of the matter that was in the log went into carbon dioxide and water that went into the atmosphere and went away. So what you're looking at is not all of the products of that chemical reaction, but just some. And that's why it weighs less. The total mass is still the same. Any questions? The law of definite proportions. So this says that all samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. What this means is if you take a compound and decompose it into its elements and find the ratio by mass, that ratio is going to be the same regardless of where the compound came from, regardless of whether it was like naturally occurring vitamin C or if it was vitamin C that was made in the laboratory. That molecule is exactly the same. And so this comes from 1797. So the example here is if we take 18 grams of water and decompose it into its elements, you're going to get 16 grams of oxygen and 2 grams of hydrogen. So we can look at the mass ratio of oxygen to hydrogen. Here it's 16 to 2, which reduces to 8 to 1. So if you took a 36 gram sample and reduced it, you're going to get twice as much oxygen and twice as much hydrogen, but the ratio is going to be the same. So let's look at this one. The mass ratio of nitrogen to hydrogen in ammonia is 4.7 to 1. If a sample of ammonia contains 10 grams of hydrogen, how many grams of nitrogen does it contain? So we don't really need a calculator here. So 4.7 to 1. So 4.7 grams of nitrogen for every 1 gram of hydrogen. Well, if this sample has 10 grams of hydrogen, that means it's 10 times larger than 1, right? So then what's the mass of nitrogen? 47. Does that make sense? We're going to be doing worksheet 2, and there's some questions about definite proportions. Pretend that you've never heard of chemical equations or of stoichiometry or moles or anything like that. Okay? These questions involve adding and subtracting, and your brain says like it's too easy. No, it isn't. This is really, really basic stuff. Okay, so here we've got 2 samples of carbon monoxide decomposed into their constituent elements. So I'm just going to take some notes here as I read this, speed things up a little bit. So one sample has 17.2 grams of oxygen and 12.9 grams of carbon. That's sample number 1. The other sample produces 10.5 grams of oxygen and 7.88 grams of carbon. So it says, show that these results are consistent with the law of definite proportions. So the law of definite proportions says that the ratio of the element masses has to be the same if it's the same compound. Right? So we can take the mass of oxygen and divide by the mass of carbon and see what we get. So here the ratio is 1.33 to 1. And here this is also 1.33 to 1. The ratio is the same. Now, if you extend that ratio out past the significant figures, one of them was 1.333 forever, and the other one was 1.33248 stuff, right? But there's uncertainty in measurements, and so we want to look at the significant figures in our answer, and so they actually are the same. Yes?
So we're always going to have a problem where it's going to be a ratio 2 to 1, right? Like it's never going to give us a ratio 2 to 2. Why is that?
That's a good question. Are we always going to be looking at a ratio of 2 elements, or could we have more than 2 elements? You can have more than 2 elements. But a ratio really only makes sense if you're comparing 2 things, right? In fact, there's a problem in the worksheet where the compound has 3 elements. So what do we do then? Well, look at the ratio between 2 of the elements and then another pair of elements. And as long as you include all of the elements at least once, you're covered. It's a great question. Any other questions? So definite proportions, then saying there's a law of multiple proportions kind of seems to contradict that, but actually it doesn't. So this one's kind of hard to put into words. If we have two elements, and they're just going to call them A and B, that form two different compounds, then the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. And this was published in 1804. So what this shows is that when we have a formula of just two elements, you can have 1 atom of A to 1 atom of B. You can have 1 atom of A to 2 atoms of B, 1 atom of A to 3 atoms of B, etc. But you can't have 1 atom of A and 2.5 atoms of B, because those are individual units. It's like saying there's 2.5 people in your family. Well, what's half a person? It doesn't mean anything, right? So it's got to be whole numbers. And so really what this comes down to is, if you look at the law of definite proportions and you find that proportion for each of the compounds, and then you take the ratio of the ratios, you get a small whole number. So let's look at that. So here we have carbon dioxide, and here we have carbon monoxide. And so if we look at the ratio of oxygen to carbon, it's 2.67 grams of oxygen will react with 1 gram of carbon. And in carbon monoxide, it's 1.33 grams of oxygen reacts with 1 gram of carbon. So we can take the ratio from the first one. You always want to put the bigger one on top, 2.67, and you can take the ratio for the other one, 1.33, and when you divide, you get a small whole number. Now your calculator might not say 2, it might say 2.0003 or something. It's going to be very, very close to a whole number. Okay, so law of multiple proportions, if you take the mass ratios of two different compounds of the same two elements and you find the ratio of the ratios, you get a small whole number. Hydrogen and oxygen both form water and hydrogen peroxide. Decomposition of a sample of water forms 0.125 grams of hydrogen to every 1 gram of oxygen. So this is water. So here we have 0.125 grams of hydrogen for every 1 gram of oxygen. And if we take the hydrogen peroxide and decompose that, we get 0.0625 grams of hydrogen for every 1 gram of oxygen. Show that these results are consistent with the law of multiple proportions. Well, this really is the ratio of hydrogen to oxygen, right? Hydrogen to oxygen. So we can take the ratio of these two ratios, so 0.125 divided by 0.0625. Oops. I'll do that on my calculator just in case the laws of math changed since yesterday. Nope. And we get 2. And the reason for that, I did H2O2 wrong, sorry. The reason for that is this has 2 hydrogens to 1 oxygen. This has 2 hydrogens to 2 oxygens. And so when we look at the formulas have small whole numbers, and therefore the ratios of the masses have to be small whole numbers. Those are fundamental concepts. There's some things in the worksheet about this. There could be a question on an exam, but then we're going to leave that behind. So if you're like, that was weird, it's okay. It's okay. Try to get your brain around it, but don't hurt yourself. Okay, John Dalton and the atomic theory. So John Dalton's atomic theory. These were his points Each element is composed of tiny indestructible particles called atoms. All atoms of a given element have the same mass and other properties that make them different from other elements. Atoms combine in simple whole number ratios to form compounds. Atoms of one element cannot change into atoms of another element. So there's a couple of things here that we needed to modify as new things were discovered. And I don't think it's in the slides, not really, no. So are atoms really indestructible? No, they're not. You can smash atoms and break them into smaller pieces. But that does not happen in a chemical reaction. So we can say these atoms are indestructible in a chemical reaction. Another thing that we'll find out is not quite right is that all atoms have the same mass and other properties. Well, it turns out that they all have the same number of protons, but their masses can be slightly different. And we'll see how that is in a minute. And then atoms of one element cannot change into atoms of another element. So a statement was added here: in a chemical reaction, atoms only change the way they are bound together with atoms. So now there's nobody arguing that atoms don't exist. The evidence is overwhelming.